Okay, so some people in the AI community want LLMs to be deterministic or say that they are deterministic. It's quite an interesting topic, so I thought I'd make a video on it. So, are LLMs deterministic? So, yeah, just got to go over the basics. So, LLMs generate one token at a time. A token is a word or a number, or basically it's just the minimum unit of output. So you can think of a token as a word. So the neural network goes through a pass from input to output, right? So one pass through the neural network produces one token. To be clear, that doesn't mean it's only thinking about one token at a time, because well, it's got a key value cache and a residual stream and all this stuff, so it's building up information as it goes, but outputs one token at a time. However, the neural network itself doesn't actually output a specific token, it outputs a probability distribution of which tokens it thinks are best. So yeah, the inference engine is the piece of software that actually manages the neural network while it's running, and it picks the token, right? So it's got a piece of code called a sampler, which selects the next token. I think the next bit is my demo, isn't it? So, right, yeah, so this script, you don't really need to know how it works, but it basically just loads a very small large language model called small LM, and we are producing one token at a time. Well, we're looking at the probability distribution, so let's start. My keyboard layout's broken again. We will start with, right, so we're going to ask it to continue. So we're basically pretending that it's already said my favorite color is, and what's it going to say next? Right. Yeah, so what we've got here is 12%, it's given 12% probability to blue, 8% to green, 8% to red, 7% to purple. So this is what we'd call a flat probability distribution, because there's lots of tokens which have a reasonably high probability, because obviously a large language model doesn't actually have a favorite color, so there's lots of viable answers, and you'll always get a long tail of really low probabilities, which the sampler will filter all this out and just pick from the top few. But anyway, let's try a different one. So this one should give us a peaked probability distribution, right? The answer to 2 plus 2 is, there's only one correct answer to that, right? So we should, yeah, so it's assigned 87% chance to 4 and 5% to 5. Now, I don't know why it's given such a high probability to 5, but just bear in mind this is kind of a stupid large language model. Or maybe it's been reading some weird material online. But yeah, so this would be called a peaked probability distribution. Did I have any more examples? This one's kind of pointless, but yeah, so the highest probability is Paris, but of course there's other ways you could continue the sentence, right? It could say it could say located, situated, named. Right, so now we're going to go back to this presentation, and so how does this sampler actually pick the next token? Well, basically it's like a roulette wheel. So back to the example where the LLM was telling us its favorite color. So basically it's like we put all of the potential tokens on a roulette wheel and basically just pick them according to their probability. So there are certain settings in the sampler that will determine how it pre-filters them. So top K means means we filter it to the top 5. Top P means anything that has, so a top P of 0.9 means anything that has less than 10% the probability of the most probable token will be discarded. So these are basically just to discard all the long tail of improbable rubbish that you always get. So yeah, this is what it will look like for a flat probability distribution. And here's the peak probability distribution. So here the top P has filtered out most of the options, because if we just scroll back up, oh, I cleared it in there. But basically, most of the options had a lower probability than 10% of the most likely token. So it's filtered them out. 3 is less than 10% of 87. So for a bigger, smarter LLM, I would obviously expect all of the wrong answers to get filtered out by the sampler, but this is a very small large language model. So what was I going to cover next? I forget. Temperature, right, temperature. So temperature is the most well-known sampling setting. So what it does is it reshapes the probability distribution. So if you set the temperature lower, basically it takes the tokens that are already likely and makes them more likely, and then it squashes everything else. So if you think of that roulette wheel, we're taking the likely stuff and making it more likely and compressing everything else. What did I write here? Yeah. High temperature. So if you set the temperature higher, it's like people say that it makes the LLM more creative, but you're kind of just making it lose its mind, to be honest. But so I think I made some pictures, right? So this is the slide I showed you earlier with the roulette wheel for my favorite color is. So if we set the temperature to a lower setting, it might look like this. So you can see the most likely token has had its probability stretched and the others have been compressed. Now if you set the temperature to 0, that's called greedy decoding, and that means you always just pick the most likely token, so you didn't even bother with a roulette wheel. Right, so can you make it deterministic? Right, so some people seem to think that it's a flaw that LLMs are not deterministic and seem to want to make it deterministic. So the most common thing people seem to do is set the temperature to 0. The other thing you can do is seed the random number generator that's used for the sampler, which basically means random number generators are only random if you start them off from a random starting point. They're actually deterministic. I suppose it's a pseudo-random number generator is what I should really say. Anyway, so if you set the temperature to 0, it kind of brain damages the model because, firstly, it stops it from self-correcting itself and makes it more likely to get stuck in loops. But the other thing is to understand is always picking the most likely token isn't the same as picking the most likely sentence. And you're kind of misrepresenting what the LLM is thinking, right? Because if the LLM is 51% certain that it wants to use this token and 49% certain that it wants to use that token, and you just always pick the most likely token, you're applying a bias over and over again every time you select a token. So it tends to actually just screw the LLM up and make it lose its mind. Setting a seed does not have that problem, but it still doesn't achieve determinism in the way people think it would or should. So I've got another demo to show that. So this is a closure script. Again, you don't need to really read the code, but what we are going to do, all this script does is it lets us call a large language model with a prompt and different sampling settings. So you can see the temperature here, which we mentioned earlier. 1 is always the default. That means you're not changing the probability distribution. If you set it less than 1, you're making the probability distribution more peaked. And if you set it higher than 1, you're flattening it out and making it more creative. Yeah, so let's start by just, so this will call Quen, asking it, would you love a monster man? I like this prompt for LLMs because they find it sort of a confusing question and they don't really know how to answer it, right? So here we've got our answer. So I'm just going to demonstrate that it gives us a different answer every time. So it often starts off, so the first few tokens are often the same, but then it quickly diverges. So if we look at the last sentence, he represents raw power and is subject to incredible movies. Here's why he'd be great, unique personality. Imagine the stories we could tell about someone with claws. So we just get a different answer every single time. So let's set the temperature to 0. So here we're basically doing greedy decoding. We're always picking the most likely next token. So the last sentence, a friendly mascot or a character. Friendly mascot or a character. Friendly mascot or character. So this is a very short output, so we're not going to see any brain damage problems here, but so that's temperature at 0, and then I'll just show that we can achieve something similar by setting a seed. So we're going to use normal temperature, so we're still doing the roulette wheel, but we're seeding the pseudo-random number generator. Wise giant, even gentle monster with heart of gold. Wise giant, even gentle monster with heart of gold. So we achieve something similar without brain damaging the model. However, here's where it gets interesting, right? If you change a single token of the input, it causes a butterfly effect that just gives you a completely different output. So let's say we just change the W to a lowercase instead of uppercase. Yeah, we've got a completely different answer. The previous one had an emoji in it, didn't it? Why is it, let me scroll down a bit. Yeah, so we've got an emoji of a dinosaur and an alien. So it's the same every time, but it's different than when we had an uppercase W. Oh, now we've got an emoji of a, robot and an alien. Didn't we have a dinosaur and an alien before? So this gives us a robot and an alien. And this gives us a dinosaur and an alien. Okay, anyway, so yeah, so the point is you've made it deterministic if the input is exactly identical down to every last letter, but you haven't actually made it deterministic in any way that's practically useful. So yes, what I'm trying to say is that trying to make LLMs deterministic is kind of futile, and I'm not really sure why people try to do it. Right, what other slides do I have? Why do you need determinism? Right, yes, so the fact that the LLM has a non-deterministic output doesn't mean that the output is wrong. and the fact of it being deterministic doesn't mean that it's right. So in some cases there are infinite right answers. So let's imagine we ask the LLM to, I don't know, write a story or write an essay about the history of the Roman Empire. There's almost infinite valid essays you could write about the Roman Empire. The other thing is that most modern large language models are reasoning models, which means they output this chain of thought internally before they give you an answer. So let's imagine you're asking the LLM to do something which has a specific right answer, like you're giving it a maths problem. Although it might have a different chain of thought every single time, a reasoning model can and does backtrack and self-correct when it makes mistakes. So you should always get the right answer, even if the reasoning trace is different. So yeah, that's it. Yeah. Was there anything else I wanted to say? I forget. I feel like there was. Yes, no, there is something else to say, and I think I mentioned this in a blog post actually. In fact, shall I find that blog post? I'm going entirely off script here. In fact, while we're going off script, if you're interested in tokenizers, OpenAI has this demo that just shows you how the LLM splits it up into tokens. So normally a token is a word, but a long word might be multiple tokens. And if you do numbers, anyway, right, so I made, it's the last post I made here. So yes, I was talking about this. So something else that's interesting is, so reasoning models, you're not really recommended to change the temperature at all, because it actually is useful for it to be able to have control over its own probability distribution. So in the residual stream, which is the an LLM basically thinks, a reasoning LLM thinks in two ways. It thinks using its residual stream, which is basically thinking using semantic vectors, doing vector arithmetic, and then it has the thinking that it does linguistically in its reasoning trace. Now, the residual stream has a representation for confidence level or certainty. So let's say it's trying to solve a complicated maths problem. It'll get like a feeling of, do I feel confident that I'm going in the right direction, or do I feel unconfident? And based on that, I mean, feeling is really the most appropriate term for it, but if you don't like anthropomorphizing it, it's a representation of the concept of confidence in semantic space. Anyway, so once it feels like it's not very confident, it can make a decision to backtrack, and it can output tokens that will then deliberately make its probability distribution flatter. So let's say it says, yes, it's here, right? So let's say it outputs the token wait, or wait, let me see, or wait, that's not right. It'll say something like that, and that allows it to then explore different options. So a reasoning model, part of its training is that it learns how to squash or sharpen its probability distribution depending on what's going on. So yeah, it's actually controlling its own determinism intentionally. It's one of the things it learns how to do. Yeah, I think that's it. And I'll call it there.